A rebooted phone will lag at the beginning and will become swift again. What if I told you your device would be more than 3 times slower if this certain thing did not exist? And Minecraft would barely touch 1 FPS without it. Ladies and gentlemen, nature is awesome. Fat is stored near our muscles for its quick disposal. Our brain is near our eyes for faster stimuli. And computers use caching. As irrelevant it sounds, it is completely logical, and you'll get it by the end of the video. But what is cache? Here's what people think when they hear the word cache. Clutter that needs to be cleared, connected to device slowdowns, taking up space on the device, something that might contain personal information they want to delete. Seems like people really hate cache. Just after the 2000s, the CPU processing speed was starting to escalate quickly, which at that time was directly dependent on the clock speed of the CPU core, which was measured in gigahertz. Meaning for faster computation, you would need CPUs with higher clock speed. But this was limited to an extent because higher clock speed meaning significantly higher power consumption and heat generation. But at the same time, there was an increase in the amount of RAM and storage, which came as a blessing. Now, I am saying this because what could not be achieved directly through high processing power was achieved indirectly using optimal memory usage. There are 3 major paths that were taken to do so. The first was used in app optimizations and process-intensive problems, which is called memoization, which sounds very similar to memorization, and really is. Here we can save results of already processed data so that when it is needed again, instead of reprocessing it, we can just pull out the saved result from the memory and continue with other things. Here is an example of 2 programs which find prime numbers up to 10 million. The program which doesn't use caching finds all in 10 seconds, but the one which uses 9.6 MB as cache finds all in less than a second. This kind of processing is not so commonly used on our devices, but is heavily used on servers to run complex algorithms or process structured data. The second one is mostly used on mobile devices to optimize app launch and save internet ingress and is not very complicated. When you open WhatsApp, there are a number of libraries and modules that needed to be loaded with WhatsApp itself and the process that needed to be started with it. And considering the number of times you open it per day, loading and unloading to clear the memory is pretty process intensive. So your operating system never unloads it or kills the process, but keeps it on your RAM. It just freezes the state of WhatsApp with keeping the notification services online. So when you opened WhatsApp, everything would just be unfreezed and would take barely any processing power to open. You'll be surprised to know that on newer Android devices, more than 1/3 of the memory stays cached when your phone is idle. There is one type of cache memory that outshines all the rest and has a significant impact on direct processing. And it's so special it doesn't even exist on your RAM, but on the CPU itself. See, when you request any data from your RAM memory, it takes time to reach the CPU, where it gets executed, typically between 10 to 40 nanoseconds. Just to make sure you're on the same ground, here is how things work. RAM holds lines of compiled program codes, which gets fetched to the CPU and executed, and does things like change pixel color on your screen, play some note via speaker, or just do nothing. And this happens in repeating cycles of fetch, decode, and execute. And the number of cycles is similar to your clock speed, which can vary from couple millions to even billions per second, depending upon your CPU. As time passed, CPU execution speeds and RAM speeds saw a huge disparity, and it was mostly due to the physical limitation of the design we used to make RAM. Our main memory used dynamic memory, which is slow, but at the same time is cheap. Then we have static memory, which is fast but also much more expensive and cannot be used to make RAM. So we basically had slow RAM. This meant CPU was sitting idle waiting for next line of code to reach the CPU core, just like you wait for a high. Now to make things faster, big brain engineers took a big brain move and built a very small static memory of couple kilobytes into the CPU core itself. And boy, don't underestimate it for its small size. Here is normal life. You open any app and first line of code gets fetched to the CPU, which takes 40 nanoseconds approximately. Then it gets executed in 1 to 5 nanoseconds, and the cycle goes on and on and on. And here is Mentos life. You open Photoshop and Blender simultaneously with 1000 plugins. And now things are different. Instead of fetching every line of code from RAM one by one and executing it, which takes 40 to 60 nanoseconds, it fetches thousands of instructions at once, and takes them near to the CPU core, into the cache memory, from where it becomes extremely fast to execute. And by extremely fast, I mean from 40 nanoseconds to a single nanosecond. These caches are divided into different levels: L1, L2, L3, L4, among which L1 is the fastest but with smallest size, and L4 with the greatest size but relatively slow speed. Whenever CPU requests some data from the memory and it's available in the cache, it's called a cache hit, and it's good news. And when the requested data isn't there in the cache, it's called a cache miss and is a bad news. Now, when a cache miss happens, the corresponding memory is loaded to cache for the subsequent usage by the CPU, which takes time but is for the better good. And commonly, the 80 to 90% of all requests done by the CPU are a cache hit, which means most of the time CPU is not sitting idle. Now, sometimes the difference between a cache hit and a cache miss is so significant that hackers can use this as a vulnerability to know what data is in your cache, or basically what's currently being executed on your device like mobile phone or laptop. After its speculative nature, the vulnerability was named Spectre. It essentially works by checking how much time does it take data to reach the CPU, by which it can deduce if the data is on the cache, which is indicated by smaller access time, or not. And once it goes, well, it's not really a game over, but you also cannot prevent it from doing that because it's not a flaw, it's a design marvel, just like nuclear power plants and nuclear bombs.